So just to set the expectations extremely low, I put this together in just a couple days, and it's a little bit random, and it will not, unfortunately, my learned friend at the end of the table, it will not help you to program very well today. It's mostly about to show you what's possible, and you go, learn for yourself some of these things. So there's an extensive references on the last slide that you can copy down, or I'll email it to you if you'd like. Okay, so the plan is we're going to talk about functions, where they come from. We're going to talk about that in both mathematical and programming contexts. And then we're going to talk about 4 things that are kind of aspects commonly associated with functional programming. We'll talk about dispatch tables, memoizing, map grep, and other list operators, and then finally currying. So we'll start here with maths. So on the top there, you see a function. It's called f. F takes an argument x, and the function is defined as x squared. So this is something that people doing algebra right now, 8th, 9th, 10th graders would be learning. We have another function g, which is defined as 2x, so twice the value of x. Algebra allows you to compose functions by passing in functions as an argument. So you can see we're going to define a new function called h of x that is defined as f of x, whose argument is g of x. So let's pass in g of x, which we know is 2x from the second row. Let me see if I can get a cursor here. Here's g of x, 2x. We're going to take this 2x here and stick it in right here into f. F, we know, is defined as x squared, so we're taking this and we're going to square it here. When you work that out, it turns out to be 4x squared. So h of x is 4x squared. You don't have to feel comfortable with this. I totally get that. I just want you to know where these functions kind of come from. We can evaluate functions now by passing in actual integer values. So if we passed in a g of 3, that's 2x, so that's 2 times 3, that's 6. 6 gets passed into f, which is a squaring function, so we have 36. If you notice, though, our composed function h, we can also pass in a 3 down here. And that's defined as 4x squared, so we take our 3, square it, which gives us 9, multiply it by the 4, and we also have the same, we wind up with the same value. What's neat here is that h of x is a function that was defined through another function. We passed in g of x into the first function and got out this second function. So it's a function maker. So functions can be used to make new functions that are equivalent to the composition of the smaller functions that you use to compose them. So in computers, we also use the word functions. In Perl, we call them subroutines. And so we're going to talk just for a moment about functions and how, some of the things we use functions for, right? Computers need lots of detail. And I had a job interview a little while ago, and somebody asked me, I want you to tell me how what happens when somebody makes a web request from their web browser. Well, it's turtles all the way down, right? First, they type a key. Well, there's an interrupt that handles that keystroke. I mean, all the way down to the electronics, right? Then all these electrons pass over the wires, right? I mean, it's amazing the level of detail that happens to make it work. So we hide all of those details using functions when we get up to the programming level language level. Functions allow us to avoid that complexity by abstracting, pushing away, and hiding the details of what's really going on. Good functions make it clear what's actually going on. Good functions will just do one thing, one useful thing. Good functions don't have side effects. They don't do anything secret. And a good function will take, if it's like a method, an object method, it will take 0 arguments, maybe 1 argument. That's called arity. Maybe 2 arguments, something like that. But past 2, it's no longer a good function. So let's see. Let's say we wanted to make a calculator, okay? One of the common ways to do this, I'm not going to say it's the best way. Is this, can everyone see that? Is that large enough? Okay. So we're going to start with a little while loop here. The diamond operator reads in from standard in, or whatever you're piping to it, actually. We're going to chomp off the line, so this will leave us just a clear line with no new lines at the end. And then we're going to pass that. I'm sorry for the brevity here. I just had to make it fit on one screen. We're going to split that argument, which is going to be, this is what the line is going to look like. We're going to pass the function we want to do first, so addition, and then we're going to pass the arguments. So it works like this. So if we wanted to add 4 and 5, we do a plus 4, 5. If we wanted to multiply 4 and 5, that gives us 20. If we wanted to do 2 to the 8th power, that gives us 256. And we can do 100 divided by 4. Oops, I didn't do that right, did I? We're going to do divide 104. And there we go. And then we can quit. So there's our little function. It's cute. It's a short little while loop here that will loop forever. The calc function is where all the magic happens. We accept the function, so this would be the plus symbol, and then the 2, and then the 5. We check to see in our list if the function was quit. If it was, we exit. If the function was something else, we do something else. So this would be a nice novice approach to this.
It's bad. It's got 3 arguments.
Yeah. Besides, it is taking some arguments. I thought I was going to have to clean my glasses. That looks so much better. Thank you, Doran. Okay. So this is not good. It's not just that it's taking multiple arguments. We'll give that a pass, but it's the whole if structure. There's a cleaner way to do that, and that's called dispatch tables. This is what a dispatch table looks like. We define a hash called my cursor up, funcs or functions, whatever. And its key is the function we want to do. So in this case, we have quit, we have the plus symbol, we have the minus. I even added a Fibonacci here. And its value is a subroutine. So the subroutine, when you dereference the hash value, or when you what is that called, Ryan? Where you give the hash its value and or its key and it returns the value. The value is, gentlemen, is a subroutine reference. So what does this look like? Look at number 2 here. So we're going to do the same thing. We're going to read in. Nothing's changed here in this section. But what we've done is we create our dispatch table here. And then, I'm sorry again. This is the brevity thing here. So we actually create the dispatch table on the fly. And then we immediately pass in the key. That key returns, so let's say that func is going to be like plus or minus or divide or multiply, whatever that is. That's going to return a subroutine reference. Oops. It's going to return a subroutine reference, say this line here. And that subroutine reference we immediately invoke and pass the remaining arguments, so like 3 and 5 or something like that. So it works the same way. We have Fibonacci here. So let's try the Fibonacci. 2 fib. So does everyone know the Fibonacci sequence? It's kind of a recursive function that it's a mathematical sequence, and it calculates it. It's kind of expensive to calculate here. I added some debugging statements here so you can see some of the problems that I've created by this. We're creating the dispatch table every time we call the function. And Fibonacci is being called every time we run it. So if we do fib 6, fib 10, fib 13, fib 15, fib 19, it's starting to get slower.
What's the stack overflow limit again in Perl by default?
I don't know.
100.
Is it?
But it's just a warning.
Fib, what did we do? 24?
I just used to have
Fib.
throw 101 in there.
Well, we need to finish tonight, so I'm not going to do that. Fib 27, we're getting, you can see how long this is taking now. A lot of that's mostly I/O, but it's taken a long time to calculate these things.
Recursion is a poor way of solving Fibonacci, even though it's simple. Right?
Yeah, you can see the Fibonacci is really elegant here. We fib returns a subroutine. To calculate it, we pass in, we call it with one argument less plus the two arguments less. That's the definition of Fibonacci. So this clearly has some problems, and that leads us. So this is a dispatch table. Yay for dispatch tables. They're nice and clean. You can see one nice thing per line. But it leads us to our next thing that we want to talk about, which is memoizing. Memoizing is just locally scoped caching. There's nothing amazing about it except what it can give you in terms of speed. So we're going to memoize our function here. So this hasn't changed, except that the first thing we do is we take our original calc function and we pass it to memo, which returns a reference to a subroutine. And that's what we're going to invoke instead of the original calc. The original calc is unchanged. I haven't changed anything. Memo works like this. Memo takes a function reference, which is calc. It creates a cache. And then it returns a subroutine. And the subroutine is what's interesting here. What the subroutine does is we're going to be passing it the same arguments we used to pass. So fib 25 or plus 35, whatever that might be. It joins all those arguments, and we call that our signature. Then it takes that signature, and that's the key now, into the cache hash, and we set that to the value. We set its value to be the calling the function, unless it already exists. If it already exists, then we just return it here. So let's see how that does. Here's the memoized function. We're going to say calc 3. You know what? Let's move to the top of the screen here. So plus 3, 5. Very nice. So create the dispatch table. Let's do fib 10. OK, let's do fib. Am I doing the right one? Yeah. Let's do fib 30. Oh, very fast. You can see that it's not doing all the recursion anymore. What it's doing is the ones that it hasn't seen before. And the nice thing is we can go, what did you say, Ryan, 109? 101. It's a big number, but it solved it like that.
Sweet.
Now, why is that? What we're doing is we're trading space for time. Every function call that we make gets stored in this hash. So if somebody said, what's 3 plus 5? Well, we go, OK, well, just a second. I'm going to store 3 plus 5 and call the function. I'll tell you what that is, but I'm going to save that so that next time you ask me what 3 plus 5 is, it's just a hash lookup. So we trade up memory for speed. So in the Fibonacci sequence, which is an extremely expensive operation, every call depends on the two previous calls. So we can say Fibonacci 100, but we've already calculated everything up to it before. And we don't have to do it every time. We just did it the one time. So there's 100 entries in our hash table when we do fib 100. That's nothing. That's easy. That's a nice one, a nice trade-off. Now, memoizing is not always the right solution because some calculations are faster than hash lookups. A hash lookup involves all kinds of complex cryptographic functions to make sure you don't have, there's a lot of math going on there. So if you're just storing the result of 5 times 8, 5 times 8 is going to be faster to calculate than the hash lookup itself. So, be aware of that trade-off there. But by and large, if you're doing anything expensive at all, memoization is amazing. And you can see that it doesn't take, it's one extra function here. And in fact, CPAN is full. In fact, I think built into core is memoize. Yeah. But this is poor man's memoize here. You take your original function, and now this is memoized. You call it exactly how you used to call it before. It's cheap, easy, and excellent. Okay, now we're going to move to the third of 4 items that I was going to tell you about, map and grep. Most of you will already know this, but for those of you who don't, it is a kind of a foundational thing with functional programming. The first thing we're going to do is make a list of 10 things in the list. This is the range operator. It just expands everything between the one end and the other. So this gives us a list from 1 to 10. And we're going to store it in list. Map is a function. Map and grep operate from right to left instead of from left to right. So you have to read these backward. What map does is it takes things on the right side, does something to them, and shoves it out the left side. And that's what gets assigned to double here. So in this case, we're going to take every item in the list, its alias to $_. We're going to multiply that thing. So the first thing, what's the first thing? It's 1, right? So 1 comes into this little function here. This is a bare function. 1 comes in, we multiply it by 2, and that gets pumped out the list and pushed into double. Then 2 comes along, 2 comes along, we double it, it becomes 4. 3 goes into the little function, it gets doubled. So at double is now a list of double all of our original list items. You can also do a little bit more complex things like, here's some unencoded UTF-8. We can now, or Unicode, we can now encode those into UTF-8 and pass it out the other side into this list here. So you can do some very powerful things there. Grep is kind of like map. Things come in from the right side, but the only things that come out the left side are when this expression here is true in Perl truth terms. So if we pass in a 1, we do 1 modulo 2, that was the remainder 1. That's true. 1 is a true value, and so it gets shoved out the back here. 2 gets pushed in, 2 modulo 2, its remainder is 0, and so it's a false value, so it doesn't return anything. So this gives us, this is a clever little way to get odd numbers from a list of numbers. For evens, we can do the same thing except invert the sense of the test here. So that's map and grep. Yes?
My favorite thing about map and grep, map will always return the number of elements passed in or more, and grep will always return the same number of elements or less.
Yeah, good to keep in mind. Thank you.
Unless you return parentheses from map.
Yeah.
Yeah. And it flattens. Okay, the last thing I told you I would talk about is currying. So currying is named after Haskell B. Curry, 20th century mathematician. It is the same Haskell of the lovely functional programming language. So let's pretend we have a program and we want to do some logging. Okay, so let me put our calculator here. Here's a little program. We're going to set our logging level to 3. Right, this is poor man debugging, poor man logging. Everyone does this. We print out some stuff if the log level is above a certain threshold. We call some useful function, and then we have some more debugging. Maybe inside of our function we've got some logging as well. I don't know. So how does this run? You know, like you'd expect. You get some print statements. That's nice. But we immediately see we can do a much better job. It'd be nice maybe if we, instead of getting all this boilerplate, stay, standard error, if level 2, why don't we put that into a function, right? So it might look something like this, where we call our function log with 2 G's, because log is a mathematical function. So we pass in our log level and the thing we want to say. So when log is called, we pass in its level. We can skip it now. So that's nice. That's an improvement. We're now much shorter and cleaner looking. Most people could look at this and say, oh, it looks like we're making a log something, but what's this 2 thing? What's this 1 thing? I don't understand what that is. So we can probably do that a little bit better. So what we might consider doing is putting some of this into named subroutines, right? This is a common path. We'd have a function called debug, info, debug, and these are defined as, these are just little wrappers around log. So you can see we're abstracting this in a good way, and we're adding a little bit of cool stuff. We're adding some extra stuff that we can, let's see how that one looks. Oh yeah, see now we got a nice timestamp and this kind of thing and our log messages. That's nice. But you can see there's still a lot of boilerplate. All these three functions are almost identical. So currying, see if I can get this going here. Currying looks like this. We're going to look at it first. Let your brains settle around it a little bit, and then we'll talk about it. Currying is the idea that you remember in our very first, when we were talking about math, we had a function that returned another function. That's what currying is. Currying is a function maker. So what we do here is we have we're going to call a function called logger, and it's going to take the level, and then we're going to what loggers are going to return is a subroutine. So trace, $trace is now a subroutine that makes trace messages. So, and debug is a subroutine that gives us debug messages. So here it is right here in action. We have debug and starting program. So you can see how nice that is. We're not passing anything extra to it. It's very clear what's happening. I'm not putting this forth as an example of the right way to do logging. This was a contrived example to show you how to do currying, but you can see the benefits of very small subroutines that these are three loggers that we've defined. Anyone can see that.
So doesn't your useful break down a little bit?
Sorry?
Your useful sub, which was also doing its own logging?
Oh yeah, I've kind of dropped that off here for the sake of visibility. These are lexically scoped, so it would work the same way in there. So yeah, at the end we'll talk about object-oriented and functional and how they interplay. Okay, so logger. Yeah, so we're going to talk about currying here. Currying is a currying function accepts one argument, and then it closes over that argument with a function that accepts additional arguments. It's called a closure. It's not that scary. We'll look at it in detail here. And it's also this is also called partial evaluation when you do that. You take a single argument, close over it. That's the one that got evaluated. The rest of the arguments have not been evaluated yet until the subroutine fires off. So curried functions are function-making functions. So let's look at this one more time. What we have here, this is our currying function, logger. You can see that we read in level, and then based on what level is, we either return an empty subroutine that doesn't do anything. Oh, I thought I fixed that. That should be if, and this should be reversed, but you get the idea. Otherwise, if the level is correct, if it's above the right level, then we return a subroutine that joins all of its arguments and prints them out. So that works like this. Yeah, so here it is in action. Oh, here's where I fixed it, right down here. So very nice. I removed the little nice textual things, but they could be put in with a little lookup table as well. So we have now a function-making function. It creates three functions here. Whoops. And we can now invoke them. It's really nice. Okay. And one last example for currying. Remember, I know that you'd probably like me to go into more detail. This is really I'm just trying to whet your appetite, because there's so much to functional programming that you really need to sit down with it and spend some time learning it. But currying, once you've learned currying, it changes how you see everything. You want to use it for everything. It really makes for some nice, clean, easy to understand abstractions. Okay, last example, we're going to look at a web client. So we're going to use the modulus user agent client because it's really easy. It's very small. So we create the user agent here. This is not currying, by the way. This is just normal stuff. So we create the user agent. We invoke its get method on this URL. And then we have to pass in this big fat header because we have basic authentication going on here. And we're going to print it out. So what does that look like? Oh, I hope I'm on the network. Yay, I am. So what this does is it makes two user agent calls. It makes a get and prints it out, and then it makes a post and prints it out. Okay, so this is fine, but what we see, what's one of the problems here? There's a lot of boilerplate going on here, right? You've got this whole authorization header thing for every request. Really? That's horrible. So what would be nice, what we realize is that maybe we can abstract some of that. We'll make a little function called transaction, and it takes our arguments. Let's say that we wanted to, instead of invoking the get method or the post method, we want those as parameters so that they could be put into variables or something like that, right? So here's the first argument, the second argument, and the third argument is a hash reference for the headers here. This works the same. We make a transaction, we start it, and then we get the results back. So this is just one step out that someone might do when they don't want to use dynamic methods. They can just use the same method, transaction, and pass in the arguments. But we still have this boilerplate of we're passing in the authorization header to every call. So this is where currying can come to the rescue here. What we do is we make a basic auth transaction maker, and we pass it the basic auth headers. So here's what that looks like. We grab the headers, and then we return a subroutine. This subroutine is a closure because we're closing over headers. This subroutine accepts a method URL and a body. And then, oops. This is not closed over from the outer. Just this one is here. So this headers is closed over here. It refers to that. So that was created at the time the function was defined. The rest of these happen when the function is called. That's what the currying does. So now we have a function here, BATX maker, basic auth transaction maker. And when we invoke it, we pass in the method and the URL and maybe a body, and that gives us an actual transaction we can use. So now our functions are much smaller. They don't have any boilerplate. Things that you would duplicate from function to function are great candidates for currying. Things that happen everywhere. Throw those into a function maker so that you don't have to see them again. And again, this would normally done like maybe in a library or something, so you don't even have to see this. But so what you wind up with is a function maker. And I think that's it for now. Are there any questions about this? I know we went through that pretty fast. I wanted to make sure Dave had some time. Questions about currying? Oops. Okay, we're going to skip that. Okay, so functional programming, object-oriented programming, people will get in fights all the time, but they don't have to. They're equivalent expressive power. They're both trying to achieve the same goal, which is abstraction. That's why we make functions in the first place. It's to hide things we don't need to worry about right now without hiding things that shouldn't be hidden. Object-oriented programming is not, it's a tool, and it is often misapplied into domains that don't fit the object model. And functional programming is the same kind of way. You see all kinds of crazy stuff going on with functional programming to sort of get the same benefits that you get from objects. It doesn't have to be that way. They can play in the same space. You can make curried methods, and your objects can work with functions as well. Sometimes it is about the data. When it's about the data, that's a great place that's where functions really shine. So that is all I've got tonight. Here are some references. these are great introductions to functional programming. I highly recommend Higher Order Perl. Mark Jason Dominus. It's a free PDF, and a few people have converted it into EPUBs and Mobis and other things like that, so you can stick it on your electronic device. Modern Perl by Chromatic is also a free ebook. Excellent. And then the standard SICP, this is how you learn to make a scheme compiler, a scheme interpreter, beg your pardon. But I mean, there's a lot more to it than that. This is the foundational book. For many years, this was the MIT Introduction to Computer Science handbook, and they just recently finally got rid of it, but it had been in use for 20 years or more. It's a phenomenal book. So,
They switched over to Python.
yeah, great choice. So
Indeed.
that's it for me.